Welcome back to the second part about the details of the Allegro A1335 precision Hall effect angle sensor. In part 1 we started writing our own library for that thing, and we got so far that we were handling the 5 most important primary registers in that chip and got in a controlled manner angle readings from it. Card here. Link in the description. Now there are 4 other primary registers left, and I want to cover those in this video. Enjoy! Let's dive right in with the first one, the temperature sensor register. So that starts like all the other, or most of the other registers we've already seen, with a register identifier, which is in this case 1111. Followed by 12 bits of an unsigned integer temperature. And to calculate the temperature in Kelvin from that unsigned integer value, you just divide it by 8. The public interface to the temperature register is quite simple. So we have, like always, a Boolean read temperature that does the I2C communication, reading the 16 bits of data from the chip. If that fails, returns false, we can use last library error to get a clearer picture of what went wrong. And then we have 3 functions here. Temperature Kelvin, that gives you the temperature in Kelvin, temperature in Celsius, which gives you the temperature in Celsius, and temperature raw, which gives you that 12-bit unsigned integer. There is, of course, a bit mask here, a private constant for the 12 bits of the temperature inside the temperature register. The implementation of these methods in the CPP file is equally simple. So read temperature does the usual. It does the read primary register with the temperature register address and our private temperature register buffer variable. And if something should be wrong with the register identifier, then we raise a library error bit register identifier code and return false, otherwise true. Temperature in Kelvin uses the temperature raw function, which we will have a look at in a second, and divides it by 8. Temperature in Celsius uses temperature Kelvin and subtracts 273.15 Kelvin from the Kelvin value. That yields you the Celsius value. And then we have temperature raw, which does nothing but taking the content of the register, which we just read by the read register function, and binary ends that with the bit mask for the temperature, so the last 12 bits. Quite similar to the temperature register is the next one, the field register, which starts with the 4-bit register identifier code 1110 and then a 12-bit unsigned integer that contains the magnetic field strength. And yeah, no scaling necessary here. That's directly the field strength in Gauss. The public methods in our class for the magnetic field register are quite similar to those of the temperature register. So we have a read field, returning false if something fails. And then we have only one function here, field Gauss, that returns you the field strength in Gauss. Of course, there's another private constant here, primary register field strength, that contains the 12-bit bit mask here for the field strength within the field register. The implementation is of course also exactly the same like for the temperature register. So we have a read field that reads the register and then checks the register identifier code, etc. And we have that single function field Gauss that simply returns the private buffer variable for the field register, binary ended with a bit mask for the field strength in that register. Then we have the error register, mask register. which contains a lot of bits you can use to mask out errors in the error register, so they won't show up in the general error flags within the status register and the temperature register. It also starts with a register identifier, in this case 1100, and that is followed by exactly the same flags you also find in the error register. We had a look at that in part 1 in detail. Please note that you cannot mask out the extended error flag here, which is set if there's any unmasked error in the extended error register. The public interface for that register really consists of a single function mask error that gets a bit masked here with the errors you want to mask. And of course that function writes over I2C to the device and returns false if anything should go wrong. It uses the same unscoped enum here error we already introduced in part 1, which defines all the error bits. And please note again, you cannot really mask the X error bit here for the extended errors. Again, a trivial implementation in the CPP file. We just take here a buffer variable and fill that up with a register identifier code for the error mask and binary all that with the error flags, which we pass as an argument. And then we write the whole shebang over via I2C to the chip. Finally, we have the extended error register mask register, which works exactly the same like the error register mask register, but for the extended error register. So register identifier code here is 1101, and then you find all the flags of the extended error register. If you mask out all of the extended errors, the extended error flag in the error register will never be set, and thus no extended error will ever raise the general error flags in the temperature register and the status register. The public interface is exactly the same like for the error register mask register, just that we add here everywhere extended, okay? And hopefully you remember that unscoped enum here, extended error defining all the extended error flags. And I won't explain the implementation in the CPP file. It's, yeah, exactly the same like for mask error. Now, for a little test sketch. I simply take the sketch we've already seen in part 1 and extend the loop by also reading the temperature from the left and the right chip and the field from the left and the right chip. And I also print out these values to the serial port. Please note I'm scaling here the temperature in Celsius by a factor of 10 up and the field in Gauss by a factor of 10 down, so it will fit into our angle in degree scale from 0 to 360. And that's how the whole thing looks on the serial plotter. 6 lines in total now. So the first line, blue, should still be the angle of our left sensor. Yeah, that's okay. And 0 detent. And then red is the angle of our right sensor. 0 detent here. And if I just bend back and forth the left breakout board, we should see, down here, we should see a change in the magnetic field strength. So that's lilac. And on the other side, right sensor, yeah, we see the same. Works perfectly. Now that leaves us with the orange line and the green line. That should be the temperature. Let's see if we can do something there. Oh yeah, So green is the temperature of our left sensor, and obviously while blowing at it, I was cooling it. I mean, it's at about, approximately 35 degrees, and ambient temperature is about 30 degrees. Yeah, I'm sweating here. But yeah, my exhales are still below the chip temperature, so it's cooling it. And we saw I also hit a little bit the right sensor. Let's try that directly on the right sensor. Yeah, wonderful. Okay, I guess everything works as expected. I know, that was a rather short video, but that's quite okay because I'm still extremely busy with work, and so this will give me some breathing space to actually implement access to the extended 32-bit registers of these chips, which will unlock a whole slew of functionality. So in part 3 we will have a look at those registers. Till then, bye!